Okay. So in any pulley problem, which by the way are so common in first year physics, in every single unit, they will give them to you in forces, in energy, in work, in momentum. The whole course sometimes revolves around a lot of pulley problems. Okay. All right. So in any pulley problems, what are the like some of the basic objects that have to exist in it? Well, obviously, the first thing is you need a pulley. Okay. So what's a pulley? Basically, a pulley is what? It's just a circular disc with a groove in it that the string could basically fit in, and it becomes the connection mechanism. Which means the second object has to be what? Has to be a rope or a string or a chain or a cable or some sort of a connection mechanism between the objects. Which means the third thing has to be what? Two objects. By the way, technically you can have what? You could have what? How many objects in a pulley problem? But that means you have to act as the other object, pulling down on it or pulling or releasing up. Okay. But we're not going to do almost any problem with someone pulling, although we could. We're just going to hang two objects and let them, basically pull each other. Finally, the fourth thing is something we could add to the problem to make it more physically complex. We could add what? Surfaces. Okay. And surfaces, whenever they're added, what do they add to the system usually? Again, normal force, or also what force as well? Friction. There you go. So if we want definitely to add more complexity to the problem, we would definitely make the objects touch or move along surfaces. Okay. That's all you have to copy for this slide. That's all you have to copy for this slide. Now, a couple of important things, everyone. A couple of important things about pulleys. Uh, about pulleys in grade 12 versus first year and second year and so on. We always make two assumptions in introductory physics, especially grade 12, about what? About pulley problem. Number one, the pulley is massless, which means what? What does massless mean? Has no what? Has no mass. Is that even possible? No. But what does that mean? When you say an object is massless or negligible mass, what does that mean? The mass of the pulley is what compared to the object, to the masses of the other blocks and stuff? Big or small? Insanely small, that it doesn't what? It barely affects the what? The motion of the system. Also, it has no what? What's axle? What's an axle? Whether you talk about, like machines or cars, what's an axle? Yeah, Muhammad, go ahead. Yes, exactly. An axle is basically what? An axle of rotation. So basically, if you really have a real pulley, 3D wise, it would look like this, right? And then you have what? What goes through here? The what? The axle. So basically, the axle is what? Is the rotation? What is the rotation rod that actually what? That basically this goes through. Does that make sense? Okay, we assume that there is no what? No friction between what and what? The pulley and the axle, which means when it turns right here, is there any friction in this region right here? Is there really? Okay, by the way, if there is really no friction, if there is really no friction, how easy is it to spin the pulley? Very easy, right? Because again, remember, when there is no friction, you can what? You spin one thing, and basically it just keeps moving forever. But the thing is then, this axle could also what? Not move because there's no friction. So we assume there's what? There's no axial friction, which means there's no energy loss. Energy loss due to the what? Due to the rotation. Okay. So this makes what? This assumption makes dealing with friction easier and ignores how really hard it is to what? What's another word for spinning? Torque. Force when you spin is always called torque. Okay, the will of the pulley. The second thing is also the string rope is also what? Massless, and also what? Has no axial friction. Because when you put the rope, where do you put the rope? You just make it what? Hang on the what? Hang like this. And from the other side. Does that make sense? We also assume that there's no what? Actually, sorry, this shouldn't say axial friction. The pulley is not touching, sorry, the string is not touching the axle. The string is touching the what? The pulley. So everyone, sorry. Uh, Scratch this and write pulley friction. My bad. Pulley friction. Yeah, there's no point of making the string touch the axle. It doesn't. It touches the pulley. Okay? Same thing. This means it makes it easier to ignore any effects of what? Of the mass of the rope. Because everyone remember, when an object pulls another object through a rope or via a rope, it also is pulling on the what? On the rope itself, which means the mass of the rope technically should be incorporated. Well, we're going to assume it's so light, it doesn't what? It doesn't need to be incorporated. Okay? All right. By the way, both of those assumptions are not made in what? In which year? First year physics. Because in first year physics, they will teach you about a very important kind of motion that sadly is not in grade 12 anymore, which is angular motion and something called angular momentum. Like how hard is it, not just to push something, but also to what? To spin it. So they will teach you a lot about torque. I'll actually show you a couple of university textbook chapters completely devoted to nothing but torque. Okay? All right. What is the easiest kind of pulley you can make? You can just have a what? A pulley, a rope or a string, two objects, and no what? No surfaces. So the easiest kind, it's kind of like this. Okay? So basically, here, if the two objects are the same, if the two objects are the same mass, doesn't matter the size or the dimension. If the two objects are the same, and you hold them and then you let go, what's going to happen? No, there's no movement. Why? Because basically both of them are pulling on the rope exactly the same way. So one object has to be what? One object has to be even slightly heavier than what? Than the other one. So let's see how we can do a very basic pulley example. This is the easiest pulley problem you can ever see because it's just the bare bones of it. Okay, so consider the following system. All right, I think you have the system. Yes, you do. So we have two objects. What's the mass of the object on the left? 3.2. How about the object on the right? So right there, if I'm holding both and then I let go, we know for sure which way is the system going to spin? That way or that way? Exactly. So that means the 5.4 is going to what? Is going to pull the 3.2 up and itself will move down. By the way, would you call that a clockwise or a counterclockwise spin? Yeah, exactly, because it's going what? With the clock. If there's a clock there, if you go right, it goes clockwise. The question is always the same. By the way, it never changes. Find the common acceleration of the what? By the way, why is it common acceleration? Again, are they connected using a string or a spring? Can you imagine what would happen to these two if they're connected using a spring? Question, everyone. Okay, has anyone seen the demo where you hold a spring and then you let go of the bottom end? Does the top end start moving immediately? Immediately with the bottom end? What happens to the bottom end first? It has to what? It has to extend enough, and then it pulls on the what? It pulls on the what? On the top end. So that's why we never connect them with what? With springs. We just connect them with what? With strings, because that means once an object moves, the other one also what? Moves exactly with it, the same way, the same speed, the same acceleration. So the question is, what's the common acceleration? And then what? How much tension is throughout the whole string? Okay. How many objects do you see in this problem? How many people say 3? How many people say 4? Technically, there are 4 objects, right? A pulley, a rope, and 2 blocks. But which 2 are the really important ones? They are basically the ones with masses in them. The ones that are subject to F net equals. By the way, is this F net equals 0 or F net equals MA? Right there. It has to be MA because I'm asking you for what? For acceleration. If their acceleration was 0, that would be what? F net equals 0. Okay. So so how many FBDs do we need to sketch? 1 or 2? 2, because the object of one is going to affect the what? The object of the other. Has to be. By the way, if you cut this, what's going to happen? Does this even know about this now? So with what acceleration exactly? 9.8, you guys. So basically, the existence of this one will still make this one move, but at faster or slower pace? Slower pace. There you go. If you cut, then they have no connection. Okay. How is this 5.4 is going to move? Up or down? 5.4. Down. So go ahead and put a down motion arrow this way. Motion. Which means here we put what sign? Positive. Thank you. Okay. Can someone tell me what are the only 2 forces on the 5.4 kilograms? Yes. Tension and gravity. So Fg. By the way, let's call this mass 1 and let's call this mass 2. So go ahead, just put a 1 here. Just put 1 on top of the 3.2. And just put 2 on top of the 5.4. So as Wadah said, this one's got to be subject to FG2. And question, should we say T1, T2, or just the same T across the whole thing? Same T. By the way, okay, when you consider torque, then you consider what? Different tension here than tension here. But when you do not consider torque, we actually have the same tension felt inside the entire string. So just go with T. All right. How about the FBD for the second one? Almost the same thing, but one thing's got to change, which is the what? The motion direction going up. All right. So go ahead. Motion direction going this way. Plus motion. Technically, is it the same two forces as well? Yes, it is. Fg, but Fg1 this time, and same tension. So T and Fg. Sorry, Fg1. Done. Okay, now let's go to the next slide. Full marks for the FBD. There's absolutely nothing more that you have or need to show. Okay, so let's start with mass 1. Everyone, mass 1. Oops, sorry. Mass 1. Mass 1. Come on. Is it F net equals 0 or F net equals MA? Great. Go ahead. Again, you can say, oh, accelerating motion implies second law. No, just say F net equals MA. F net equals MA. All right. Now I need someone to tell me what are we gonna write on the side, the left side, which is the side for F net. Look at the FBD and basically ask yourself, how many forces are there? Which one is pointing positive? Which one is pointing negative? And literally just write them on the left side of the equation. Ahmed. So plus, so in wait, okay. Mass 1, is it moving up or down? So which one is winning, tension or gravity? Tension. There you go. So tension is positive. That's why we said the direction of motion to be positive that way. So plus T minus Fg what? Fg1 equals technically M1, because it's only this mass of relevance. Do I need a acceleration 1, acceleration 2, or do they both have the same acceleration? Again, they're connected with strings, so they move as one single train, one single unit. What's my next step? Every time you see Fg, what do? Mg. Technically, by the way, technically it is what? Ma. But the A in this case is a very special what? 9.8. You see what I mean? Fg equals Mg is a very special case of F net equals Ma when your A is what? Free fall 9.8. Okay? Yep. So T equals, sorry, I mean T minus M1G equals M1A. How many unknowns do I have in this equation? Unknowns. No point. 2. What are they? Yeah, the two things that the question is asking for. I have no idea how much tension is in the string, and I have no idea how much acceleration the system has. So that means what? Can I solve this, or does it have to wait? It has to wait. You can never do anything with an equation that has more than one unknown in it. What is that I? That's 1 in what? In Roman numerals. All right. What's my next step? I don't have a choice. I have to go to what? Mass 2. All right, mass 2. Is it still F net equals ma? Of course, if one part of the system is accelerating, anything else connected to it is also accelerating as well. So F net equals ma. Okay, who would like to tell me the second line for that equation? أوضح? Yes, now gravity is winning. So plus Fg2, yep, equals technically M2A. Same thing, M2G minus tension equals M2A. Again, how many unknowns? Box again. Box. and number 2 this time, Roman numeral. By the way, I don't care if you use regular 1 and 2, but a force of habit, I guess, is used to use Roman numeral. Remember the two methods of solving any system of equations from grade 10? What were they? We discussed them yesterday. Substitution and which one is always more powerful in physics, especially when these things happen? Why? Josh, tell me what there can eliminate itself, or does eliminate itself, actually. Tension. By the way, if you ever, listen up, if you ever have a tension problem and you do not get tension in one part of the equation to be what? And the other part to be what? Because tension on one object is winning, but on the other object is what? It's losing, which means for one of them, it's pointing with motion, but for the other one, it's pointing what? Against motion. Done. Tension always eliminates itself, which is, by the way, why I always ask you for what first? Acceleration. Because when something is eliminated, it doesn't get evaluated then. You have to do the subbing in after. All right? So now what do? Nothing. You just do the addition line. Okay. What cancels itself, as you said? Tension eliminates. So if you basically drop everything here on the left side and drop everything here on the right side, tension drops with a plus once and a minus once, which means it eliminates itself. So what survives on the left-hand side? From the left-hand side, original one. Yep, an M2G with a positive minus M1G with a negative. So M2G subtract M1G equals, by the way, we're adding. We're adding. Never, by the way, never in elimination, you never subtract. You just what? You just add. Because why? Because you are banking on the fact that the minus added to the plus will kill each other. What's the right-hand side? Yeah. M1A plus M2A. What's the only unknown in all of this equation? The only unknown. Acceleration. Perfect. This equation is definitely what? Solvable. Can we plug the numbers now? Can you? Can we do some math thing to simplify our life? Just raise your hand if you see it. Can you do any math thing here to simplify your life? I mean, you can plug in numbers. Please go ahead. No problem. But okay, what if this question had no numbers? What if I wanted you to say, what's acceleration in terms of all of these things? Like a symbolic equation, which, by the way, quite common in first year. What do you do when you have common things in math? You common what? You common factor. You common factor. What's a common factor on the left-hand side? On the left-hand side. The G's. What's a common factor on the right-hand side? Great. So let's pull a G from both of these things. So G. So what survives inside of the bracket? Come on, this is grade 10 / grade 11. M2 minus M1 equals what? What do you, A? Or I like to write the A at the end. Doesn't matter. Who cares if the bracket is before or after? So what's A equal to? What divided by what? What? Symbolically. By the way, in grade 12, I make a habit of always training you with the symbolic first. Because trust me, that's what next year is going to have you do. Yes, Amar. Uh-huh. Yep. Divided by. That's it. G M2 minus M1 over M1 plus M2. Okay, I need someone to help me with this. Obviously now, I can do a very quick subtraction here, a very quick addition here, and then multiply and divide. By the way, question to everyone. What if M2 is equal to M1? Come on. What's going to happen? Even without me knowing the numbers. What if M2? If M2 is equal to M1, what happens to this one? 0. Does it matter how big this one gets? 0 divided by anything is what? Which means what? Does the system move? No, it doesn't. Perfect. You see? Conceptual analysis. If the two masses are the same, there should be absolutely no acceleration, which is, in other words, no motion. Okay. M2 is what? 5.4, I think. M1 is 3.2. So go ahead. Come on. Subtract, then multiply by 9.8, and then divide by the addition of both masses, like the mass of the whole system. Again, everyone, if tension doesn't cancel itself throughout the math, you made a mistake. because that means it might not be positive and negative. It might be both positive or both negative. Tension always cancels out because tension is Newton's third law. It's always what just connects. Hmm. Let's hear two numbers here. Sorry, the number twice, just to confirm. By the way, could it be 9.8? Could this acceleration of the system? Why not? Because the only thing that moves at 9.8 is an object what? Free falling. No, those are not free falling because they are both connected. What'd you get? So Josh got 2.5. Anyone else? Perfect. And the sig fig situation is 2. So 2.5 in what unit? It's acceleration. So it's what? Meters per second squared. And that's it. That's it for part A. How do you do part B? What is part B asking for anyway? Tension in the string. What do you always do with elimination or with the system of equation once you know one variable? You plug in. Now, technically, either equation works. In fact, you could do both, or you do, although you don't have to, just to check. But which equation is easier to use for tension? Why the first one and not the second one? Exactly. If you're going to use this one, you're going to have to do some algebraic movement of this here and this here. No, always use the one that's easier what algebra for you. So now we're going to plug in 2.5 all the way up in equation 1. So I'm going to do it in a different color. So I'm going to go green. All right, so now T equals, I'm going to move it already, M1. By the way, what's a common factor here between these two once I move this one here? M1. So M1, and since they will be both positive, G plus A. Done. So it's what? What's M1? 3.2? 3.2 times, don't forget the bracket, 9.8 plus 2.5. How much is that in newtons? Because it's a tension force. Well, definitely 30 something. Yeah, go ahead. I moved it. I am. I moved it, which means it will be M1A plus M1G, and then I just did the quick factoring of the math. Make sense? Yep. What's the answer? 30, 39.36, but according to the sig fig situation, it will be just what? 39, just because of two sig figs. Done. Welcome to the most basic pulley problem. That's it. Two objects, one string, and we're done. Here. You can change mass 1. You can also change what? Mass 2. And you can also change what? Coefficient of friction, depending. If the system is already in motion, then what coefficient of friction are you playing with? Mu k. If the system is not moving yet, and you're investigating if it could move or not, then you're playing with what first? Mu s. Also, you could play with the what? With the angle, and you could produce something like this. We're not going to do that today. You could produce something like this. Boom. Look. Just like that. All right? So let's do a basic problem first. Sorry. So let's do, nope, not this one. Nope. Also this one as well. Actually, this one is a calculation. Everyone look. This one is a calculation website. Got so many topics, and people actually like built in, kind of like, you just change the numbers and you click enter, and basically it already has all the equations, in the background in the actual HTML code, and it basically just just gives you how much tension and how much acceleration and all that stuff. Okay, so you can always check your answers. It doesn't show you the steps, but at least what confirms your final numbers at the end. Okay, all right. Okay, so what do we have here? How many blocks do we have? Still what? Yeah, there's no point of having a pulley problem with one block, unless you are technically the other force on the other side of the string. Two blocks are connected by a massless string that passes over a frictionless pulley. Again, if those two things exist, that means we don't have a problem, because no such thing as a massless or a frictionless pulley. We're just simplifying the physics and the math. The coefficient of what? Coefficient of what? Static friction between, obviously, only M1 and the table. Obviously, is there any friction here? Not unless I make it what? A perfect wall, and this what? Rubs against basically the wall as it goes up and down. Nope. I mean, we could introduce that to the system, but let's just keep M1 just the friction one. 0.45. The coefficient of what? Kinetic friction is how much? Point what? Which makes sense because mu k is always less than mu mus. Mass 1 is 45 kilos. Mass two is 12 kilos. I know it doesn't say what the question is. The question is basically, does the system move or not? That's it. Does the system move or not? Okay. So first of all, how many objects do we have? 2. Can someone tell me what forces are on this one? Gravity and what forces are on that? Always start with the most basic one. Gravity, normal. Now, if this is to move, by the way, could this ever move this way on its own? No way. Friction does not pull things. It just resists. So if this one is going to move, which way is it going to move? Which means tension definitely is pulling it, if anywhere, pulling it this way. Which means if this is not moving, which way is friction acting? The other way. All right. So let's go to the next slide. Okay, go ahead. FG. Sorry, FG2. Come on. FG2. How about this one? Again, do we have 2 tensions or just 1 tension? By the way, in these problems, by the way, did we have a problem where we actually had T1 and T2 before? Yes, we did. What problem? The elevator one. But why? Because did we have a single rope going through a thing or 2 different strings? One from the top of the elevator to the first block and one between the first and the second block. Perfect. No, but this is one single piece. One single piece has the same what tension experienced in all of it. So go ahead, T. Come on, T. Okay. How about here? Well, FG1. Do you need to call it FN1? Because there's only how many FNs? 1. So they're just FN. There's only one table surface interaction, FN. Tension. Okay. Let's say it's FS. Let's say FS. By the way, is there an equation we have for FS? I know we don't know yet if it's moving or not. What's the equation for Fs? What's the only equation that we learned that includes Fs or Fk in it? The mu s, right? Mu s equals Fs over Fn. All right. So, question, everyone. How would this system, listen up, how would this system stays in position? How would it stay in position? That means all the forces have to do what to each other? If nothing is to move, all the forces have to what? Have to equal or cancel out, which means the Fg2 has to equal what? And tension has to equal what? Which means Fs has to equal what? Does it make sense? Transfer. If this is equal to that, and this is equal to itself, and this is equal to this, which means what? Okay, everyone, what if Fs is bigger than Fg? It's not going to move. What if Fg is bigger than Fs? Then it's going to move, okay? So, first of all, let's calculate what? Let's calculate Fg2. So, did you say why? Yeah, okay. Again, this whole problem is literally a tug of war between what? Between Fg2 and F what? Fs. Okay, question. If I make this surface really, really, really rough, is motion going to be easier or harder? Which means what? If I really make this a very hard surface, should I use a smaller mass or a lighter mass or a bigger mass? Which means this one could overcome what? That's why I'm saying what? It's really a war between friction and gravity, right? Okay, so let's calculate Fg2 first. So Fg2. What's Fg2? What's the equation? Fg. M2g, which is what's mass 2? The hanging mass, not the table, the hanging. 12, all right? So 12 times 9.8. How much is that? Well, that's very close to 120. Actually, it's 117.6. Sorry, not 117. Or 117? 117.6, yeah. Okay? Let's calculate Fs. Who remembers the equation for Fs? which is really the cross multiplication of the original equation of mu s. Mu s times Fn. Yes. Mu s times Fn. What can you say about Fn and Fg1? Is that table block moving down? Is it moving up? So right off the bat, what can you say about the normal force on it and its own weight? They're what? Which means I can replace Fn with what? You got it. Yeah, but that's why you need to sketch what? FBDs. They will lead you through. Equals. Oops, sorry. Equals. US times FG1 equals US times M1G. All right, now we can do the calculation. What was the mu s? The static kinetic, so the static friction coefficient. 0. Oops, my bad. 0.45 times 45. Thank you. Times 9.8. Who's got this? Come on. Yes, Ahmed. How much? 198.45. Oh, what do you have? How many people got 198.45? Okay, 0.45 times 45. What'd you do? I'm just interested. Uh, oh, okay, that's why you got what? 5% extra, basically. Yeah, perfect. Does this system move or not? Who wins? Everyone? Who's winning? Gravity or friction? Friction. Which means what? To get the system to move, what do you need to do to it? How many things can you do to this system to allow it to move? Again, there's a bunch of things you could do. Ammar, give me just one thing. You can, which mass though? Of object 2. Because if you increase it, which one of those two numbers increase? That one. Okay. What else could you do? Josh. Uh-huh. So, oh, okay. What if I just want to start it to move? Well, yeah, I want to start it to move. Go ahead. Decrease what? Interesting. Decrease the what? Decrease the mass. Okay. What's the third last thing I could do? Wadah. Exactly. Decrease the what? Don't decrease the mass. Decrease the what? Like the question you had in your quiz, right? You had a question in your quiz that basically told you what's the effect really of the mu s. Does mu s depend on the mass? It depends only on the what? On the surface system. So you can either what? Use a lighter mass, because when you use a lighter mass, are they pushing too hard on each other, or you release it a little bit? Which means what? It's not what? It's not interlocking as much. Or you could make it ice, which means then you're playing with what variable? The mu s. Or you could make it what? Or you could do a bunch of things. But at least if you're doing a control experiment, one of these three things will work. So let's do a therefore statement. Therefore, everyone, therefore, friction is large enough to, I'm not gonna say to stop motion, because technically there's no motion, but to what? To keep the system to keep the system stationary. Okay, to keep. Sorry, Ahmed, what did you say? To prevent motion. Thank you, everyone. To prevent motion. Thank you. Much easier. Prevent, which is weird. I did use it to define it 2 days ago, but I forgot it now. Prevent motion. You see, get used to these problems where they give you an extra piece of information like mu k, and yet it has nothing to do with the problem. Extra information could sometimes be given to see if you know what needs to be used and what doesn't.